In this video, we're going to be calculating empirical formula from experimental data, including metal oxides, water, and salts containing water crystallization. First, we'll look at the terms empirical formula and molecular formula. We have a question here. I just want you to pause it and read the question and try to answer it on paper. So for the first answer here, this tells us, the molecular formula of benzene tells us that in a molecule of benzene there are 6 carbon atoms and 6 hydrogen atoms, whilst the empirical formula tells us the ratio of carbon to hydrogen atoms, so there's 1 carbon per hydrogen. For sodium chloride, its empirical formula is NaCl, however it doesn't have a molecular formula. That's because sodium chloride is an ionic structure, so it forms a giant ionic lattice, so they are no molecules. It has a high melting point. Here are your answers. Okay, here we're going to calculate the empirical formula of magnesium oxide. To do that, we need to find out the mass of the magnesium and the oxygen in our product here, in the magnesium oxide in the crucible. Now, to do that, first we need to find out, we need to write down the elements, magnesium and oxygen here. And the first thing we're going to find out is the mass. Now, the mass of magnesium we can find out from the experimental data here. And the mass of magnesium, the first one, we've weighed the mass of the crucible, that is 32.46, and then we've made the mass of the crucible plus the magnesium. So this has been added. So the difference between these two is going to give us the mass of the magnesium, and that is going to be 0.24. And we can just put that straight into our table. And then the mass of the oxygen, that's going to be the difference between, so we've added magnesium here and we've weighed the difference. Then here, we've actually got the crucible plus magnesium oxide after the reaction. So the difference between these two values is going to give us the value of this oxygen here. And the difference here is 0.16. I'm just going to write it here. We then need to find out the MR of each of these atoms, of each of these elements, and you can find that out in the periodic table. It's 24 and 16. We're looking at the top number in the periodic table. You then need to work out the moles, and to work out the moles you need to know the equation that we learned in the last video, that is moles equals mass over MR. And to work out the moles, we just need to take the mass and divide by the MR, which is simple. Now, doing this, you'll get 0.01, 0.01 for this. Now, we then need to work out the ratio. So we've got the moles. We've got 1 atom of magnesium reacts with 1 atom of oxygen. So 0.01 moles of magnesium react with 0.01 moles of oxygen. Therefore, our ratio is going to be 1:1. So our empirical formula is going to be MgO. It's a 1:1 ratio. Very easy, this one. When we do this experiment in real life, we don't always get good results. That's because some of the magnesium oxide powder might escape when the lid is lifted. Not all magnesium might have reacted, or the magnesium can also react with nitrogen in the air if it's hot enough. We're going to now calculate the empirical formula of copper oxide by reduction. This is similar to the last experiment that we just did. We have copper and oxygen. Those are our 2 elements. Now we need to find out the same values that we had before. So we need to first find out the mass of the copper and the oxide, of the copper and the oxygen in here. To do that, we look at our results. So we had the mass of the empty dish first, then we had the mass of the empty dish and copper oxide. So we had plus copper oxide here, and then here we had just the mass of the dish plus the contents at the end of the experiment. At the end of the experiment, the oxygen reacted with the hydrogen forming water, and that leads on to our next experiment, but we just had copper remaining. So to find out the mass of the copper, we need to do this value minus this value. So these two values minused, and we're going to get 2.54. To find out the oxygen, we need to do these two values, the difference between these two values, and that is going to be 0.64. We now need to find out the MR of each atom, and the MR of copper is 63.5. Look at the top number in the periodic table, and oxygen is 16. Then we need to work out the moles. Again, like in the previous slide, we used the equation which you should know at your head. Moles equals mass over mR, and we're going to get here 0.04. You can type that into the calculator, 0.04 here. So our ratio is going to be 0.04 divided by 0.04 is 1, and 0.04 divided by 0.04 is 1. So our ratio is 1 to 1, and the empirical formula for copper oxide is CuO. Okay, this is the same experiment that we did with the slight that we just did just now, but it's with a slight twist. So the reaction that is happening here is we're adding a stream of hydrogen into the apparatus, and it's going to be reacting or reducing the copper oxide, and that's going to form water. So that hydrogen is going to react with the oxygen to form water, and then copper is going to be by itself, and that's what we weighed afterwards, the copper. Now, instead of that water just leaving the tube as water vapor, we're going to collect it in the U-bend here and weigh it, and we're going to try and find out the empirical formula of the water as well, and that's going to fulfill this part of your spec. So if we look here, we've got exactly the same experimental data from last slide, except we have water here. So we have the mass of water here. So before we did plus copper oxide, and then afterwards we just have copper, as we've just said. We had the difference of these two. We said that the difference, or the mass of the oxygen, was 0.64. Now, to find out the empirical formula of water, it's exactly the same as what we've been doing before. We need to first write the atoms or the elements in. So we have hydrogen and we have oxygen, and we again need to find out the mass, and then we need to find out the MR, sorry, and then the moles, and then the ratio. And then we can find out the empirical formula. So let's find out the mass of the hydrogen. So if we have the mass of the oxygen, which is here, and then we have the mass of the water, which is here, if we minus these two, the difference between these two is going to be the mass of the hydrogen. So the mass of the hydrogen is going to be 0.08. If that's a bit difficult, just pause and just trying to get your mind around that. Then your mass of your oxygen is 0.64. And then again, this is exactly the same as what we've done last time now. So all from here, it's plain sailing. We've got 16 moles. I'm not going to write down the equation. We just do 0.08 divided by 1. That's 0.08. And this one is 0.04. Now here, this is the only different thing now, that we have a ratio. Our ratios, because the moles are different, we need to find out what our ratio is, and to do this we can do 0.08, and we can look at the moles and look at which one is the lowest number and divide both numbers by the lowest number to get our ratio. So if we do 0.08 divide by 0.08, we're going to get 1. If we do 0.04 divide, it's 0.04, we're going to get 2. If we divide 0.04 by 0.04, we're going to get 1. And you can just look at the moles and see that for every 0.04, per every oxygen, there's twice as much hydrogen. So you can see that there's a 2-to-1 ratio there. You don't need to do it like that. But for numbers which are a bit more difficult to see, the ratio, then you can just divide by the smallest number. So we've got 2-to-1 ratio here. Our formula of water is therefore going to be H2O. Last but not least, calculating the empirical formula of salts containing water of crystallization here's a definition of what water crystallization is as a reminder. Now, this is quite similar, except for we are working with atoms. We're working with molecules instead here when we're trying to find out the empirical formula. So we're trying to find out this N here. And so we need to find out what the ratio of barium chloride is compared to water molecules. So we're not working with atoms, we're working with molecules here at the top. So, but other than that, the procedure is exactly the same. So the first thing we're trying to find out is the mass of each of these. And then we're going to be working out the MR. MR is a bit more complicated here. Sorry, before it was the AR, but here it's the MR. I've said MR, but I meant AR in the previous ones. And then mass MR, and then you're going to be working out your moles and then your ratio. And then you should get the empirical formula at the end. Okay, so let's see what we've got. So mass, to work out the mass of barium chloride, we need to, so here we've got the mass of the crucible first, great. Then we've got the mass of the crucible at the bottom with the anhydrous barium chloride. So the difference between these two is going to give us the mass of barium chloride. That's going to be 2.08. Now the mass of the water is going to be the difference between these two. Now we've got barium chloride, we've got hydrated barium chloride in the crucible. Now when we heat it, this water here is going to be driven off, and to ensure that all of it's driven off, or we've got to keep heating it until it stops changing mass. So we say that we're heating to a constant mass here, and that's how we know that all the water is gone. So the difference between these two is your mass of water, and that's 0.36. Now we can write that here, 0.36, then MRs. Now to work out the MRs is a bit more complicated because we've got molecules. Now working with barium, the MR for barium is 137 plus 35.5. We've got times that by 2, and when we put that into the calculator, we get 208. Now for water, again, we've got to calculate it, but it's 18. Now to work out the moles, it's exactly the same, mass over MR, and we're going to get 208 here. We're going to get 0.01. and then we're going to get 0.02 here. Now to work out the ratio here, you can probably just see the ratio, but I'm just going to go with the calculations here by dividing by the smallest number, just so you get some good practice there. That's going to equal 1, that's going to equal 2. Now we can now see that our barium chloride, the formula for this salt is BaCl2. We put a dot there to separate them, and then we're going to have 2 H2O molecules trapped in that crystal structure. Okay, I've got lots of practice for you to do. This one's slightly different because we're working with percentages, but don't worry, we're working with percentages. Just take that to mean mass. So you can just do exactly what we've done before, putting in the atoms here, and then instead of mass, you're going to have percentage. So mass or percentage, it doesn't matter. It's the same thing. Okay, I'm going to give you, take as long as you want on it, and then pause the video and then look again for the answers. Okay, here are your answers. Just check to see where you've gone wrong. I would say always include your working out. So again, pause this, give it a try. Okay, so here are your answers. Just one thing to note here, which you may not have come across before, is that when we did our mole ratio, we got an uneven. We didn't get a whole number here. We got 2.52. So to make that a whole number, because you can only have whole atoms, we have to times both of these by 2 to get your simplest whole number ratio, which is your empirical formula. And that's the same with this bottom one here. Again, pause and see if you can get it. This one we've got 3 or 4, so this one's a bit more difficult. Okay, so you should have got something like this. Again, here this is a bit of a weird one, but we've rounded down because even though it's not a whole number, it's close enough. Again, we've got one more practice here. I hope you're still laying it out exactly how we've done before. Okay, here are your answers.